this recording. All right. So good afternoon. So I don't know if you saw, but I finally marked assignment 1. It took forever, and because I'm, reading everyone's assignments, and then anyways. So what I've decided, I don't know if you guys have used Gradescope in the past. It makes my life a lot easier. It makes your life a little bit harder because you have to hand stuff in on Gradescope. So I'm sorry about that. But it makes my life a lot easier for marking, and especially for consistency. I like to use it because it lets me grade just one question at a time. So everyone's question 1 and then everyone's question 2. Oh, so you have used it. Awesome. It is really nice. And once you get the hang of it, how to hand stuff in. Oh, nice. Let me guess. Was it Steve? Steve got me hooked on Gradescope. That bugger. Oh, nice. Yeah. Yeah. So, oh, that's so fun. Steve and I sit like right next to each other in our office usually. So I usually just turn around and I'm chatting with Steve all day. And so he got me hooked on Gradescope when it first came out. And I was trying not to use it because I don't know, it can be difficult to explain to people what to do, but if you can believe that, it is. And so if you haven't used it before, we're going to use gradescope.ca, not gradescope.com. And so we will start submitting assignments on Gradescope. So if you go to gradescope.ca, and that's going to be important because there was one time, so when I first started, there was only .com, and then they introduced the .ca one, so that's great. So that's the one that we want to use. And then I had people trying to sign up on different ones and it wasn't working. But once you get there, let me see if I can, did I write it down somewhere? I don't think so. I just created this course for us because I thought, you know what? I'm just going to do it. See how it goes. Let's see here. Oh yeah, so our entry code, make an account if you don't already have one. That feels pretty obvious. And then the entry code is MZ5579. Let me go back to you guys here. Okay. And that should put you into the course. Yeah. So try that out. I put up a kind of a folder for assignment 2. And so upload your work. And select either the pages. Oh, that's totally fine. Welcome. We're going to be using Gradescope. That's what you missed. And if you haven't used it before, it's just an online submission tool that helps me mark more consistently, but also a little bit quicker. So you upload your work and then select the page that corresponds to each question. So give that a try. What I'm doing for assignment 2. So assignment 2, I think, is due tomorrow night, right? And so you can submit it. You can upload it to Moodle still if you want to, just kind of in case. But I want you to try to submit it on Gradescope, just so we can get that up and running. And then if I see that you're up and running, then that's good, right? So try that. But just as a fail-safe, I'll keep the Moodle Dropbox open for this one. And then for the future assignments, then we'll just do them through Gradescope. Okay, good. Good. Was there anything else I wanted to say, kind of admin wise? I've decided that we're going to do test 1 after section 2.2. 2.2 is on transformations, but for more than one variable. So we've seen transformations already, and then we're going to do it for more than one variable. Lab tomorrow. I'm really having a hard time figuring out what's appropriate for the lab, but I think it doesn't hurt to keep working through those lab videos that I have available on YouTube already. And so for this week, you can consider it a break if you've already worked through some R labs and that kind of fun stuff. But I want you to do lab 4. So it's called lab 4, and it also works out to be lab 4. I was looking at that document. I must not have posted the most recent version or something. It all looks the same, but lab 2 and 3 look very similar, but I'll have to look into that. But I want you to, for the lab this week, because I'm really struggling to figure out what we should be doing for the labs. And so kind of play it by ear. I don't want to use all of the lab time to just cover class material, because that seems boring. So we'll sprinkle in some of these R labs, which I think are quite a bit easier than the class material that we're doing. Yes, it is the course outline, and it should be in the first block of the Moodle page. But I'll have a look here. Yeah, it's under week 1, the Stat 240 outline. In fact, let me pull it up here. The labs, just as a reminder, the labs are 15%, assignments 20%, the 2 tests for a total of 30%, and then the final exam 35%. Let's see if I can get back to the meeting here. Okay, so that's kind of just off to the side here. And our final exam, we said last day is on December 8th. Oh yeah, so what I want to do is, it's okay if for some reason you've already worked through these labs, maybe in Stat 230, but then a lot of people, it doesn't seem like they have, so because there's no lab component for Stat 230, so it depends on who you had. And if you have, then that's totally fine. Just take the win and just have an easy lab. That's okay. So for the lab this week, do lab 4 from the lab manual. Right, I will post a link to the video on Moodle. Okay. So how can I highlight this all? There, I did it. Okay, so that's what we'll do. So I'm around if you have questions in that time, but otherwise it's just work on your own, right? So work on your own. No in-person labs, but I am available if you need me. Okay. So I'm around, I'm, working on other stuff here, but so I think that'll be good, right? And so if you have a question, then just let me know. It doesn't have to be during the lab time even. Right. Okay, I think that'll be a good, I like that it's an easy task for you guys. So, or it should be relatively easy compared to the other stuff that we're doing. So in terms of review, let me just flip back here. We started talking about distributions of two random variables. We won't do too much review. Distributions of two random variables. And we talked about now we're going to have some joint PMF or PDF. And we said, okay, a PMF is for a discrete function and a PDF is for a continuous function. And then we're going to have some joint CDF. And that's for either one, right? And the CDF is the cumulative distribution function. And so we started talking about the joint PMF, which is for a discrete function. So we looked at the discrete case and we also looked a little bit at the CDF, but it gets a little bit tricky, right? Because X can be, X is some random variable, and let's call it Y as the second random variable, right? X and Y, maybe I'll clarify that here. X and Y, or X1, X2, Y1, Y2, it doesn't matter. Right, two random variables. And they can be measuring, or they usually measure two different things, right? So then X is going to have some possible outcomes and Y is going to have some possible outcomes. But then we can also look at, oh, good question. No, I don't think so. Off the top of my head, you're not going to have one discrete and one continuous, because what would that look like? I'm going to say no for now, but I reserve the right to change my mind if I come across something. How about that? But yeah, so the problem that we saw was, yeah, plus a continuous variable, but then we would treat them individually. So then it wouldn't be a joint. That's a good question. Off the top of my head, yeah, because you would treat those as two separate things, but yeah, I'm sticking with my no, but reserving the right to change my mind if I come across something. Oh yeah, so that's what I was gonna say. So X is gonna be changing, Y is gonna be changing, and then we need to look at all the possible combinations of these outcomes, right? And then also even harder is the joint CDF, where we look at, okay, X is going to be changing through its possible outcomes, and then Y is going to be changing through its possible outcomes. And we need to consider all the different scenarios. Right? And so let's see here. We looked at the example, and I think that's where we got to. We ended up and we said, in general, for for two discrete random variables, discrete, let's see if I can. Then we have the probability that, and these should be capital XY, is in some space A, is going to be, so the probability that some combination of X and Y is in some space A, that's hard to think about, but is just some outcome essentially, is the sum of all the X's in A. Okay, and so all the possible combinations of X and Y, and maybe I put a bracket here because I had it in the notes there, but I actually think should go there. So all the XY combinations in A, right, so that satisfy that criteria A, we sum over those and we sum the PMF, the PXY of X, Y. And we saw examples last day, but today we're going to move into the continuous random variable. So we're going to start by looking at two continuous random variables and see that it behaves the same way, but now instead of a summation, right, for discrete random variables, we're always going to be summing. And for continuous random variables, now we have to integrate, right? So I want to take a little bit of time slowing down to integrate here in case that's been a while, right? Maybe it has for me. So that's why I feel like we need to take it nice and slow, but maybe you guys are calculus masters already. Get your calculus saber after Calc 4, right? Two continuous random variables. So what we said in the discrete case was we could look at the CDF just like we did for example, the Z table, right? We could find probabilities using the CDF, but now it doesn't really lend itself to that anymore, right? And so we're going to find the same thing with the continuous case, right? But we're just going to put it out there and say, that's not really what we're going to be doing, although it's an option, but it's a little bit harder. So what I've got here is just like in the discrete case, we could consider the joint CDF which we denote by a capital F, right? The CDF is always a capital F. F, X, Y, X, Y to define a probability. Density function. Sorry, my intonation was not good there. Right? How did we find the PDF, right? Because now we're talking about a PDF for a continuous random variable. So how did we use the CDF to find the PDF? Well, we have to take the derivative of the CDF, but that gets a little bit tricky, right? Because now I have an X and a Y variable that I need to deal with, right? But we could, and that's why I've underlined here, we could do this. That is an option, but it's typically not what we end up doing. So we could find the PDF fxy of xy is the derivative of fxy del x del y. Okay, and my del's always look like 2's, and I always struggled with that. That looks even more like a 2 to me, right? But here, this is a partial derivative since f has multiple arguments. So this is a del. Which is a kind of a delta. Okay. Like I said, it's not something that we're going to gravitate towards. So we're just going to leave it there, right? But I'm just saying that you could take the derivative with respect to x and then with respect to y, right? Because both x and y are in there. So we could do that, but it just gets a little bit weird. So in practice though, we will start with the joint PDF. Start with the joint PDF rather than differentiating the joint CDF to get it. So we'll start with the joint PDF rather than make that look like rather than differentiating the joint CDF to get it. Okay. So what we can do is once we have, so if we're going to start with the joint PDF, and this reminds me, actually, I posted 2 documents at the top of our Moodle page. So kind of random, I should have said it at the beginning, but let's see if I can find our Moodle page here. Just want to show you. So here at the top of the page, at the bottom of the top of the page, I posted a list of common distributions and also a calculus reference page. And if you've used Stewart's calculus book, which you probably have, then these will look familiar, but it's nice to have them handy. Okay, and so here it lists all the possible PMFs and PDFs as appropriate, but also the moment generating functions. So we can use these later on, but it might be nice to have these and just kind of flip through them. Okay. And also the calculus reference pages might look familiar. I just stole them from Stuart. It was just 10 pages, so it won't hurt him. Right, specifically, once we get into, well, if you need a refresher on derivatives, right, differentiation rules, then and then the integrals. Some basic intervals or integrals, but also some more advanced integrals, right, that might be useful. Okay, but I'll point you towards the ones that we'll need and that we'll rely on. Okay, good. Glad I remembered to show you guys that. Okay, so what we can do is we can use this joint PDF, right? And we can find probabilities. Okay? And so we can use the PDF. We can use the PDF to assign a probability for the random vector xy to be in some region, now, because we're looking at two variables, an x and a y variable, to be in some region of the xy plane. Okay, so now what that translates to is the probability. So now we're going to develop the continuous version, the probability of x and y in some space A. It's going to be a double integral where x and y are in A. And we're integrating the PDF again, just like in the one variable case, right? fxy of xy dx dy. Yeah. So if we want to put some bounds on here, right, instead of talking about xy in some space A, what if we have some rectangular space, right, where x runs between A and B? So for example, for a rectangular region, which might look like this, x is between A and B, and y maybe is between C and D. So now I can create this region, region. Okay. And I should clarify that, of course, this is the x-axis and that's the y-axis. So if we wanted to find the probability of being in this region, what could we do? Well, we could differentiate, we could integrate over x and then over y, and then that would be the probability. And so what we would find is, and maybe I should have, let's do that, because it's all part of the same example. So I just want to have them on the same page here. So what we're going to have is the probability that X is between A and B and Y is between some C and D. I'm going to bump the equal sign over here because I don't have enough room here, but that's okay. I'm going to show that by bumping the equal sign over a little bit so that I can see, okay, this equals this. That's going to be, and maybe I'll need even more space here because it's going to be a double integral. And so I can do them in any order as long as I'm consistent, right? So if I integrate over y first, then this inner integral, give myself some more room here, between C and D of fxy of xy, right? Y is the one that runs over C to D. And so this is going to be dy. And then X runs between A and B, dx. Okay. So I integrate over y for the points of y that I'm interested in, and then I integrate that over x for the points of x that I'm interested in. Integrate over y. Then integrate over x. When do you start doing double integrals? Is it in Calc 2 or in Calc 3? I'm not sure. Anyways, for what we're doing, not that bad. You're just gonna have to, there's more stuff going on, but for what we need it for, we're just gonna focus on these kind of few instances. And so it's gonna be okay, even if you don't feel 100% comfortable with this, it's gonna be okay as long as you are comfortable integrating. Then we can make this extension to a double integral because you just focus on your y's and then you do your x's, right? Or the other way around, depending on how you want to go about it. So what we can do is we can connect the joint CDF and the joint PDF. How? The CDF, remember, is the probability of being of a value up to and including that point, right? And so now, if we let x run from the smallest possible value, which we'll say is -infinity, to some value of x, right? And we let y run from the smallest possible value of y, let's say it's -infinity, up to some value y, then we have this kind of joint CDF. We can connect the joint PDF to the joint CDF by considering the event where x is less than -infinity up to and potentially including some value x, a lowercase x, and y going from -infinity up to and potentially including some value y, right? So now we can rewrite this this integral, this probability, right, into a CDF. So what happens? Now I can find the probability of this negative infinity to x is less than or equal to a lowercase x, and negative infinity, oops, is less than y, which is less than or equal to y. It's going to be a double integral, and I'm going to do it over y first and then over x just to match what we did before. So negative infinity to y of fxy xy dy. I should be careful. I've got a y here. This y is different from this dy. And so maybe what I'll do is I'll change these. I'm going to change these xy's to be t and u. So then here, I'm letting x be t and y be u. So then, if I'm doing it over y, it would be du dt. And I'm going to bracket off that inner integral because I'm first going to integrate over u, and then I'm going to do it over t. And t, which is the y, no, it's the x, goes from negative infinity to a lowercase x. I will make a note here that we let x be t and y be u be the integration variables. Be the integration variables. And why did we do that? Since x and y are already in use. Maybe I should explain that. Since x and y are already in use. Good. And they're in use up here, right? X and y. It would have been easier, I guess, if I had started, but this is to match the general CDF function, right? The CDF for one variable x is the probability that x is between negative infinity up to some point x, right? And so it's to match that notation, but then it kind of wreaks havoc. And so we adjusted for that by just thinking about different variables, different variable names, and that's okay. So what does this look like? Example. So consider the event x plus 2y is less than some value c, where the region of integration, looks like this. So before, right, we said, all right, I could integrate, kind of the simplest case is integrating over just a rectangle. Great. Now we're being told that the region of integration looks more like something like this. So we've got 0, no, negative c over 2, 0, and then c over 2. And then it's going to keep going just a little bit up to c. C is just some constant, right? Same thing here. If I have negative c over 2, I have 0, and I have c over 2. I'm going to take this up a little bit higher here, make room for some c. This isn't to scale, we're just doing a quick sketch here. Then the integration, the region of integration is going to be when x is 0, the y value is going to be c over 2. And then when the y value is 0, the x value is going to be c. With 2 points on a line, I can connect this. And so what it's going to look like is it's going to look something like that. Okay. Drawing lines, that's not really what we're here for, but now it helps us visualize this region of integration. And of course, this is just a quick sketch, so be careful, but not bad. So what does that mean? Well, we can take this x plus 2y has to be less than or equal to, or sorry, less than c, right? And so x plus 2y has to be less than c. And so what we want to find is, or we have, the probability that x plus 2y is less than c. Well, I can integrate and I can find, I'm going to find the restrictions on y first. Let me see here. Yeah. So then solve for y, or I guess it's a capital Y. So what do we have? We have x plus 2y is less than c, which means that y is less than c minus x over 2. All right. Which means that that's going to be my upper bound for my y. So if I'm integrating over y, so I'm going to start here, c minus x over 2, and of course, lower bound, negative infinity, because it's up to anything less than c minus x over 2. And I'm integrating over fxy xy dy, right? And that's because I solved for y. Yes, exactly. So we want to find where is this satisfied? So if we think back to that other example with the flipping a coin 3 times, right? We had the number of heads, I think it was, and then the number of heads before the first tails. So then I could figure out, okay, where is x plus 2y? Where is it less than 1? Well, with 2y, that's hard, right? Where is it less than 2? That's more reasonable, right? And then we'd have some combination of things that would satisfy that criteria. But now that it's continuous, now we have to integrate and it makes it a little bit harder. But yeah, exactly. So, so we're trying to find the probability of where that's satisfied. Good. So we have to do dy, and then we do dx. And x now has no restrictions, and so it's from negative infinity to infinity. All right. This is the same because all we did here was we said, okay, I'm going to solve for y here. What if we could have solved for x, which we can, right? And so, or we could have solved for x, but that's going to change this order here, right? And so here, because this y here, that's what dictates the dy there. Okay. Or we could have solved, or we could solve for x instead. And found that the probability that x plus 2y is less than c is, so now if I solve for x, x is less than c minus 2y. Okay. Which means that there's no restrictions on the outside of y because y is just in there. But there are restrictions, negative infinity to c minus 2y. And maybe I'll do that in light blue just to match here. And whatever whatever the joint PDF is, fxy, xy, and then dx, close bracket, dy. And again, this dictates this, right? Because this upper bound went up here, same thing here. Oh, it's a page break, so that won't be very helpful. How about that? Okay, so pretty finicky once we start this, right? But you've got two options. The only way that you're going to decide is one way is usually a little bit easier than another way, right? But you could do both. And you can do either one, it doesn't matter, but sometimes there's one that's easier than the other way. So then you would probably go lean in that direction, right? But they're the same. Okay. So what if we have an actual PDF? So here, notice we've just left it as a just any PDF, right? And so here, notice that we can use either calculation or either integral to find the probability. But often I'll say one will be easier than the other. But often one way will be easier than another, or than the other, I should say. Okay. So now, what if we introduce a specific PDF? So now we can do an example with a specific PDF. So for example, if I give you the joint PDF, consider the joint PDF, which is going to look like this. fxy, and maybe, oh. Notice that I've dropped the subscript xy. That's okay, we can do that because the xy kind of shows us that it's two random variables, probably x and y, right? And so should be somewhat obvious. I don't know, my pen is not cooperating today. E to the negative x minus y and 0 otherwise. Otherwise, then what? As long as x is between between 0 and infinity, and same thing for y. So basically, as long as x and y are greater than 0, what does that look like on our graph? Well, if x is greater than 0, it means we're on the positive x side, right? Same thing for the y's. So now we're just in the first quadrant. And that's pretty typical that we're restricted to the first quadrant here. Okay. So what if we have this joint PDF, and what if the scenario that we're interested in, what if it's x is less than 2y? Okay. And so consider the joint PDF and the event x less than 2y. Can't remember if I tried this, but it's worth a shot, right? What if I try to map I can map x is less than 2y. I was gonna see if I could map this, but I'm gonna hold off on that. I will be using Desmos in a bit, so I'm just gonna hold off on mapping it. Sorry, I jumped ahead in my brain. But the event that we're interested in is when x is less than 2y. Okay, that seems weird, but there's gonna be some region where that happens, right? And so the region, put it on a fresh page here, the region over which we need to integrate right, where x is less than 2y is, well, we've also got restrictions that x has to be greater than 0, y has to be greater than 0, but also that x has to be less than 2y. So what we can do is we can think about that region. You don't have to draw it out. It just makes it a little bit easier, I think. So here I've got my x's, here I've got my y's. And if I go from 0, 1, 2, maybe I'll do something a little bit more useful. Space them evenly here. One, 2, 3. If x is less than 2y, so my first restriction is that x has to be greater than 0. So that means that I'm not here at 0, but I'm everything out that way. And y has to be greater than 0. So I'm not at 0, but everything has to be kind of out this way, right? So then I'm restricted to the first quadrant. Restricted to Q1. And then the next restriction is that x is less than 2y. And so if I map y equals x over 2, then x has to be less than that. And so I get a point here at 2, 1, and can go from the origin. So the region that I'm interested in here, and you can check it, right? How can we check it? 2 is less than 1 times 2. No, so usually, so this ends up being a pretty go-to application. I mean, once we start looking at, for example, the normal distribution, of course, we know the normal distribution, specifically Z distributions, are centered on 0, right, with positive and negative values. So it does happen, but for a lot of these cases, especially if we're counting stuff, then you're not going to see any negative outcomes, right? So yeah, so it's going to be kind of a go-to restriction, is that both x and y are greater than 0, but we still have to say them. Okay, so where x is less than 2y. All right, so if I think about if x is 1, then yeah, makes sense, everything above. Yeah, I'm just seeing if I map the right region, but I'm feeling good. Okay, so so we can visualize this region, right? I could be bounded on this y equals x over 2 line, right? If I rearrange this, I treat the inequality as an equal sign, and then I can draw the line, and then I have to consider which region applies. And I decided that this region applies. So now I can figure out the bounds for this thing. Okay. So what we could do is we can see that, okay, well, y is bounded on what? It's bounded on, so this line is at y equals x divided by 2. Okay. So my y values are going to be bounded on what? Are going to be bounded from x over 2 up to positive infinity, right? Whereas if we did the x integral, then x is between 0 and what? 2y, right? X is less than 2y. So we're going to have 2 possible situations. And with practice, you're going to find that, okay, you're going to see the y one is, so y goes up to infinity, but x is restricted between 0 and 2y. If that answered that question. Okay, so we're going to have 2 options, right? Both of them will work, right? We only need to, the area, well, so the thing about probabilities is that it's always going to be a maximum of 1, right? And so the total area is just going to be 1, but it gets kind of mind-boggling, right? Because the area never closes, but the total area is 1. Weird. But okay, so we have two options, right? We could figure out the bounds on X and then integrate over X first and then integrate over Y. Or we could figure out the bounds on Y and then integrate over Y and then integrate over X. And so we have two options. Find the bounds on Y, integrate over Y, then integrate over X. So what would that look like? Well, Y is between, so here, Y is between X over 2 and infinity. Okay, so that would be the bounds on Y. So what would that look like? Well, that would make the probability that X is less than 2Y. I think that's what we're trying to find. Yep. Would look like this. From 0 to infinity, because X isn't going to have any restrictions beyond the ones that we set out initially. So 0 to infinity, and then X over 2 up to infinity. That doesn't look like infinity. There. Of e to the negative x minus y dy dx. Okay, that's option number 1. So I'm going to put that aside for now, and I'll just show you option number 2. We're going to work through option number 1 because it's a little bit cleaner, but you could try either one, and they're both going to work, and you're going to get the same answer. Okay, so option number 2 is to find the bounds. Wait, what the? Find the bounds on X, integrate over X, then integrate over Y. So then our bounds would be what? Our bounds would be X has to be greater than 0. That's from the first part, right? That was our first restriction. And it has to be less than 2Y. Maybe what I should do is I should put the bounds on X up here as well, right? But it's just 0 to infinity. And in this case, Y is from 0 to infinity. Well, can never draw proper infinities there. Okay, so those are our two options. And so what does that integral look like if we wanted to do it? Well, we could find the probability. So again, X is less than 2Y. The alternative is over 0 to infinity, but now going from 0 to 2Y, e to the negative x minus y dx dy. That's our other option. But we're going to work through option number 1. But you can easily kind of replicate it for option number 2. So we will do, or we will work through option number 1, right? But option number 2 will work out in a similar way. But option number 2 will follow similar steps and yield the same answer, right? So if you wanted to for some practice, right, you could try the second one and just make sure that you get the same answer. And find the same value. Okay. So if we integrated from 0 to infinity and 0 to infinity on both x and y, what are we integrating? We're integrating the entire area. So then the total area there should be 1, right? Because those are the properties of probabilities, right? If you look at all possible outcomes of x and y together, then the total probability has to be 1. But now we're putting on a restriction on either the x and the y, or x or y. So what we're going to look at is the probability that x is less than 2y is the integral from 0 to infinity, x over 2 to infinity of e to the negative x minus y dy dx. Here, what you're going to find useful is that if we can rewrite this as 2 functions, an f of x and an f of, or a g of y, let's call it, then we can we can multiply the individual integrals. That's going to play in our favor, right? Because if we have dy dx, then we can rewrite this. So here, note that just as a rule, the double integral of f of x g of y dx dy, you can rewrite, and I'm using just generic integrals here, the integral of f of x dx times the integral of g of y dy. What does this mean? It means that if we can rewrite this as a function of x times a function of y, then we can just split the integral, right? So since e to the negative x minus y is e to the negative x times e to the negative y, right? Just thinking about our exponent rules, this became f of x, and this became basically a g of y, right? So now what that means is I can split it up and I can treat those 2 integrals individually, right? It also helps to remember that the integral of e to the cx or tx or kx or whatever constant you want to use is 1 over the constant times the exponential. So also recall that the integral of e to the kx dx is 1 over k times e to the kx, technically plus c, but if you want to ignore it, you can. I shouldn't say that, but it's okay. So, right, so that's going to be useful to remember. And so here, right, if I'm thinking about integrating e to the negative x, what happens here? Well, that's e to the negative 1 times x. And so my k is negative 1. So I'm going to end up with a negative e to the negative x. Same thing for the e to the negative y, right? Okay, so here, if we start, I'm going to copy this because I can. Or you can just keep going, but I didn't want to scroll so often. So here I'm just able to keep it on the same page. So what I can do is I can show that I'm splitting. So you always want to show as many steps as you can, right? Because otherwise it gets really hard to follow. So if I've got from 0 to infinity of, and then the integral from x over 2 to infinity, e to the negative x times e to the negative y dy dx, then I can kind of group them accordingly, remembering that this first bound or this inside bound goes on the dy, or it goes with the y function, and then the outside bounds go on with the x function. So I have 0 to infinity e to the negative x times the integral from x over 2 to infinity of e to the negative y dy, and then dx. Okay. The integral of e to the negative y, we decided up here was negative, just nice integrals. So what we're going to find is there are only a few key integrals that we're going to work with. So even though it feels like a lot right now, probably we're just going to stick to some core ones. And so, yeah, when I was taking this course, I remember I don't like doing integrals that much. Any trig functions? No, sometimes we leverage trig functions, but not for us, no. So, woohoo. Unless you like trig functions, but no one likes trig functions. Yeah. Okay. I don't like trig functions. They're hard. You have to memorize them all, and no, it's not for me. But you do kind of have a core repertoire of things that you can do that we just keep doing over and over again. Okay, so what happens here is we end up with, we end up with 0 to infinity e to the negative x of negative e to the negative y evaluated from x over 2 to infinity dx. And then I'm going to have, once I plug this in, right, so e to the negative infinity goes to 0. So that's negative 0 minus negative e to the negative x over 2. Okay. 0 to infinity of e to the negative x times negative 0 minus negative, maybe I'll just do it like this, negative e to the negative x over 2 dx. Negative 0 minus a negative just puts me at positive. So then I'm here at 0 to infinity of e to the negative x times e to the negative x over 2 dx. All of a sudden, I'm at this quite simplified integral, which is nice. 0 to infinity. E to the negative x minus x over 2 puts me at e to the negative 3x over 2 dx. And once I integrate that, now my constant is negative 3 over 2. And so I have to put e to the negative 3x over 2 over negative 3 over 2, which a fraction over a fraction, I have to flip and multiply, puts me at negative 2 over 3 e to the negative 3x over 2 evaluated from 0 to infinity. Same thing again, e at negative infinity goes to 0. So then I have negative 0, which is just 0, minus e to the 0 is 1. So then I just have minus negative 2 over 3. So this is going to be negative 2 over 3 times 0 minus negative 2 over 3 times 1. This term, of course, goes to 0. Negative times a negative makes a positive. 2 over 3 times 1. I'm just at 2 over 3. Okay. So we can confirm this in Desmos. And hopefully it saved what I had. Dang it. Okay, so I'm going to put in this integral exactly what I want it to calculate. And once I finish, then it should just let me do it. So it's good that it's not there because then you can see me do it. But I'm also running low on time. So here we go. Functions, miscellaneous, the integral from 0. And then when we want infinity, you have to type it in. Infinity. And then it changes to an infinity sign. That's good. So now I'll add the other integral here. The other integral went from x divided by 2. So notice how I can put anything in the bounds. And I wish I could zoom in a little bit more here, but I don't think I can. But I'll put a screenshot in our notes. Over, yep, to positive infinity. Infinity. Good. The PDF was the exponential function, which is in I feel like it should be in stats. Is it in the MISC? Oh, there it is. It's also in the miscellaneous. EXP bracket negative x minus y. And then we wanted to do dy dx, which you're just going to type in dy dx. And it comes up with the value, which is 2 over 3, which is what we found. Now, what I wanted to look at was, can I graph the exponential function negative x minus y here? No, that doesn't help me. I don't know what I wanted to do here, but definitely what I want to do is take a screenshot of this and bring it in. Done. Saved photos. And I'm going to crop this. So that's just zoomed in on that little section, right? And so you can always confirm your integral that you've done. You can use, I mean, Wolfram Alpha or Desmos or whatever, Maple if you want. So there's always going to be ways to confirm your integral. I'm out of time. If you have any questions, let me know. Otherwise, just go ahead and work through lab 4. I'll put instructions on Moodle, but we won't meet in person tomorrow. You can just work on that lab, and hopefully that's a nice break for you. And remember, assignment 2 is due tomorrow night. And if you need an extension, I can extend it to Sunday night. How about that? Is Sunday night better? Awesome. Then I'll extend it to Sunday night. How about that? And check out Gradescope and see if you can hand it in there. All right, I'm all out of time. If you have any questions, let me know. Otherwise, see you next week. You too.